Hello all, let's start section 2.6. In my previous lecture, there was a typing error here in the topic. I typed it as a 3.4. I don't know from where it came in my mind to put here 3.4. Your previous lecture is actually 2.5, which was the chain rule. Right now, we are discussing 2.6, another topic, which is implicit differentiation. Why we call it implicit? Let's first get an idea why we call it implicit, or which kind of equations we call them implicit. For sure, in many classes, they just give you the rule. And even for some students, it's a question why I'm doing this and which kind of equations I can apply this. But let me give you an idea what is implicit equations. If I write for you y equal f of x, a function. For example, if I write y equals 3x squared plus 4, we call this type of the functions explicit. Why explicit? Because on the left side, focus, that's the thing. On the left side, you have y, not y squared, not y cubed, only y. Y equals to something. And easily you can solve this equation. Or even, because right now we are talking about derivatives, you can drive here, you can take the derivative and you can find the derivative of this function easily. This type of equations that you have y on one side, only y, and on the other side, you have x, we call it explicit. But look at this equation. For example, if I put for you an equation y plus xy equals, let's say, x squared. Can I call this equation also explicit? No, because you see, I have y here, I have y here, I have another x here. It's kind of tricky. Y is not alone in one side. But the good part is that some of this kind of equations, you can solve it for y. You can keep the y alone in one side. For example, first of all, this kind of equation that y is not alone in one side, you have other variable also on the other side. We call this type of equation implicit. Correct? But the good part, as I told you, some of them you can even solve it for y. Look here, if I take y as a common, I will end up with 1 plus x, right? Equal x squared. And if I solve it for y equals x squared over 1 plus x, then it's easy to find the derivative based on the quotient rule. But here I give you another method, which in some equations, even it's impossible or difficult to solve it for y. For example, if I put an equation like x cubed plus y cubed equals 5, higher degrees, you have to solve this equation first for y, then take the cube root from both sides. Then you have to apply the chain rule. Then you have to apply the quotient rule. Then go on. It gets really difficult to find the derivative of this kind of function, which we call it implicit equations, correct? The main idea of an implicit equation is implicit equations can be defined more than one function. For example, let me put another one for you and simplify it. If I have x squared plus y squared, for example, equal to 4. If I solve this one for y, this one will be y squared equal 4 minus x squared. And if I solve for y equals plus minus square root of 4 minus x squared. If you focus on the left side, plus minus, actually you see two functions. One of them is y equal positive 4 square root of 4 minus x squared, and the other one is y equals negative 4 minus square root of 4 minus x squared. Actually, an equation, an implicit equation, gives you two functions, more than one function. If I ask you, it's not a face-to-face class, even I cannot ask questions here. I wish this class was on like face-to-face. If I ask you, what is the square root of 4 minus x squared? Or the shape of this function, some of you may recognize that it's half circle. It's half circle. And negative square root of 4 minus x squared is another half of the circle, because we know this equation x squared plus y squared equal 4 is actually the equation of a circle, right, from algebra. But you see, for me, this equation is an implicit equation. Why? Because if I solve for y, actually it gives me more than one function. Then let me put a simple definition here for you. Implicit equations or implicit equations can define more than one function, more than one function of x. Like the one that I put here, x cubed plus y cubed. Definitely this one, if you solve it for y, it defines for you more than one function for x. That's the basic idea of the implicit equation. Now, our goal in this section is how to find the derivatives of these implicit equations, correct? I will start with one example, and I'll explain to you every single step in that example. Then we move on, and I will do a few more examples for you. Let's start with example number 1. I'll explain everything here for you. For example, if you have x cubed plus y cubed equals, let's say, our previous example 5. How to find the derivatives of this implicit equation? Let me draw here a line. On the right side, I'll write steps for you. Your step 1, or even step 1, the main important idea behind this is that you must treat y as a function of x. Definitely, y is always a function of x, right? You must treat your y as a function of what? X. Now, step 1. In step 1, find the derivative or take the derivative or drive the derivative of both, drive both sides, correct? It means find the derivative of both sides or take the derivative from both sides, correct? Step 1, take derivative of both sides. Of both side and respect to what? And respect to x. That's your step 1. Let's apply. It means take the derivative of both sides. It means d over dx of x cubed plus y cubed equals d over dx of 5. It's actually the equation rule, right? Whatever you do on the left side, you can do the same thing on the right side. If you take the derivative of the left side, take the derivative of the right side also, correct? Here you see you have the addition rule. Even I want to apply my addition rule to show every single step for you. Then I can write d over dx of x cubed plus d over dx of y cubed equals d over dx of 5. Correct? Now, look at this equation. The first part, no problem. I know what is d over dx of x cubed. It gives me 3x squared. You have enough practice. Hopefully, if you do your homework, you have enough practice to know what is the derivative of x cubed. Second part, d over dx of y cubed. Let me put a kind of symbolic form here for you. Let's say if I look for the d over dx of, let's say, let me put a function here. For example, 3x squared minus 1 to the power of 4. In my previous lecture, which was the chain rule, we learned how to deal with this function. It means the derivative of outside, which is 4 times 3x squared minus 1 to the power of 3 times d dx of inside, which is 3x squared minus 1. And you simplify this, right? You take the derivative of this part. Compare this with here. D dx of y cubed, because I told you we treat y as a function of x, then it means here I have to apply the chain rule. It means I will do this. I'll take the derivative of outside, which gives me 3y squared, times, instead of derivative of inside, because it's y, I will just write dy dx. Because here it's easy. I know what is the derivative of inside, right? I can take, but here, because it's y, I'll just keep dy dx. Remember, when you do implicit derivatives, when you use implicit derivatives, wherever that you take the derivative of y, please multiply it with dy dx. That is the rule. If you don't write dy dx, your problem is wrong. Definitely put dy dx. Now, equals, what is the derivative d dx of 5? D dx of 5 gives you 0. That was your step 1. And everything is in step 1. Step 2, even I cannot call a step 2 calculus. A step 2 is algebra. Step 2 is not even calculus. How much calculus you did? Just a step 1 to find the derivative of each term. And a step 2, solve the equation or the resulting equation for dy dx or in your book, they call it y prime. Anytime you can use the notation of y prime. Sometimes I use y prime, sometimes I use dy dx. Which way you go, they are the same. They are two different notation, right? Let's solve it. If I solve for dy dx, first I have to move 3x squared from the left side to right side. Here you go. Then I'll end up with, this is algebra, right? 3y squared equals 3y squared dy dx equals negative 3x squared. Solving for dy dx, I have to get rid of 3y squared. Divide both sides by 3y squared or multiply both sides by 1 over 3y squared. It's all algebra, right? 3y squared. These two cancels out. Here, 3 cancels out with 3 on the left side. Then dy over dx equals x squared, negative x squared over y squared. Here you go. You could find the derivative of the function, given function x cubed plus y cubed equals to 5. That is actually the derivative of that function. Correct? We call this process, this method, implicit differentiation. Correct? Let me take another example for you. Let me do another example for you. Let's say example number 2. This one is from your book. An equation is given, x squared plus y squared equals 25. They're asking you here, first, find the derivative of this function. Then, after you find the derivative of the function, find the tangent line at the point 3, 4. Even I'm not worried about second part of the problem. That's really easy. The important part is the first part of the problem to find this derivative or differentiate this equation. As you see, you have y squared in this side, then it's an implicit equation. What I do, I'll take the derivative as step 1 from both sides. D over dx of x squared plus y squared equals d over dx of 25. d dx of x squared gives you 2x. I just escaped one step. Is that okay? It should be okay, right? d dx of y squared gives you 2y, but I have to keep what? dy dx. Equals d dx of 25 is 0. The derivative of a constant is 0. Let's solve step 2 for dy dx. Then 2y dy dx equals positive 2x. If you subtract 2x from both sides, right, like this, on the other side, you get negative 2x. Now, multiply both sides by 1 over 2y. dy dx equals, here 2 cancels out with 2, negative x over y, which is the derivative of the given function. Now, here they are asking you in part B, find the equation of the tangent line at a point 3, 4. Maybe some of you think, okay, now I need a slope. Here you go, this is your slope, right? Remember my first lecture on derivatives that I told you the first derivative of a function is the slope of the tangent line. And an order pair is given to you. The first one is, of course, the value of x. The second is the value of y. If I plug these values in this equation, it gives me the slope of the tangent line. Then I can write dy over dx equals negative x. X is 3 over y, which is 4. That is the slope of the tangent line. Now, my next step is to write the equation. I will use the slope point formula. Y minus y1 equals m times x minus x1. Then y minus y1, how much is y1? 4. Equals m. M is negative 3, 4. Times x minus x1, where x1 is 3. The rest is algebra, right? Simplify. You can multiply everything by 4 to make it easy. Multiply both sides by 4. It gives you 4y minus 16 equals 4 cancels out with 4, negative 3 times x minus 3. 4y minus 16 equals negative 3x plus 9. Now, you can write here the equation in a standard form. You can write your equation in slope-intercept form. Which way you like, you can write it, right? Let's write this one in a standard form. It means I will add 3x to both sides, and I will add 16 to both sides. Then 3x plus 4y, these two cancels out, equals 3x and negative 3x cancels out, 9 plus 16, 25. This is the equation of the tangent line to the given curve, which was x squared plus y squared equals 25. That one actually is a circle. The equation of the tangent line for the point 3,4 is 3x plus 4y equals 25. Believe me, if you use a graphic calculator, or if you are really good in sketching the graph, if you sketch the graph of the given equation, which was x squared plus y squared equals 25, and if you sketch this line, 3x plus 4y equals 25, you will see your line will be just touching the circle at the point 3, 4. Correct? Do you want more examples? Let's do one more. Example 3. 3y squared plus sine y, sine of y, equals 4x to the power of 5. They are asking you here to find dy dx, or find the derivative of this function. Again, same method. Take the derivative from both sides. D over dx of 3y squared plus sine of y equals d dx of 4x to the power of 5. Now, here you are taking the derivative of y in respect to x. 2 times 3 gives you 6y, but you have to keep what? Dy dx. Plus, what is the dx of sine? The dx of sine is cosine. Cosine y. And you keep what? Dy dx. Equals right side. D dx of 4x to the power of 5 gives you 20x to the power of 4. Now solving step 2, solving this equation for dy dx. You see here you have dy dx, you have dy dx, factor out dy dx. Dy dx, parentheses, what left here? 6y plus cosine y equals 20x to the power of 4. To solve for dy dx, divide both sides by your parentheses. It means dy dx equals 20x to the power of 4 over 6y plus cosine y. Final answer. It really gets easy when you practice with few problems. Only you have to remember you are treating y as a function of x, and every time that you take the derivative of y, keep there or multiply that term with dy dx. Correct? Let's do one more example. I want to show you something else in this example. Example number, I don't know which number we are, 4 or 5, example number 4. For example, I have x cubed plus y cubed equals 6xy. Again, they are asking you here to find the first derivative of this function. It means find dy dx or y prime, whatever notation you're using. Take the derivative from both sides. D dx of x cubed plus y cubed equals d dx of 6xy. If I show you all the steps, I'll go this way. D dx of x cubed plus d dx of y cubed equals, here, when you have a constant, you push the constant or you put the constant before the derivative, keep the 6, d dx of xy. Now, on the left, d dx of x cubed gives you 3x squared plus d dx of y cubed gives you 3y squared, but I have to keep what? dy dx equals 6. Here, look at here, the important part. Do not miss it. You have x, d dx of x times y. Which rule you should apply? You should apply the product rule. Remember, your product rule is this. F times g equals f g prime plus f prime g. That's your rule, right? For the product rule. It means 6 times f. Your f is here x, and your g is y. F g prime, it means x. What is the derivative of y? What is d dx of y? D dx of y gives you 1 dy dx, right? It means x dy dx plus f prime g, the derivative of x becomes 1 times g, it means y. Now, my next step is to solve this equation for dy dx. Look, when you have a good practice with algebra, you can even do some techniques to get rid of some numbers, make it smaller. You see, here you have 3, here you have 3, here you have 6. Can I divide everything first by 3? If I do that, I'll end up with x squared plus y squared dy dx equals 2 parentheses x dy dx plus y. Now, distribute 2 to the parentheses, x squared plus y squared dy dx equals 2x dy dx plus y, plus 2y. It's all what I'm doing after the step that I found the derivative. The rest of the steps is all algebra. Now, I want to solve this equation for dy dx. You see, I have dy dx on both sides of the equation. Then what I do, I'll move dy dx, the terms that they have dy dx to one side, the terms that they don't have dy dx on the other side. It means I have to here subtract negative 2x dy dx from both sides, correct? To move it to the left. Negative 2x dy. Yeah, I shouldn't write these stuff because I just move it, but let me show you. And at the same time, I will subtract x squared from both sides to move the x squared, because that term doesn't have dy dx. I'll bring it to the right side. Now, if I do this, here, these two cancels out. I can write y squared dy dx minus 2x dy dx equals 2y minus x squared. Now, factor out dy dx in this step. Dy dx, parentheses, what left hand side? Y squared minus 2x equals 2y minus x squared. To solve for dy dx, divide both sides by y squared minus 2x. Dy dx equals 2y minus x squared over what? Y squared minus 2x. And you are done. Sometimes in your book, maybe in your homework, they ask you to find the second derivative of this function. Correct? To find the second derivative of this function, look at your right side. Just apply the quotient rule. Just apply the quotient rule. It will be the second, gives you the second derivative of the function, correct? This was all about implicit differentiation. I'll stop the lecture here. Your next topic is actually talking about applications, some kind of applications of derivatives. Applications means where we use derivatives in some problems, maybe in physics, maybe in chemistry, maybe in biology, where we use actually derivatives. That will be our next topic, and I will discuss it in my next video. For now, I'll stop the lecture and see you next time in 2.7.